All right, to wrap up section 5, we need to remember what the words and or mean. In the English language, they have a pretty special meaning, and they have a pretty special meaning in algebra as well. So in the English language, I can use the word and to join two things that must both be true. For example, the sentence, "You live in Wyoming and you are in Algebra 2" is true because "you live in Wyoming" is true, and also "you are in Algebra 2" is true. If you didn't live in Wyoming, say you lived in Colorado or something, then this part right here would be false, which would make the entire statement false. So for "and," in order for that statement to be true, both parts have to be true. For "or," one or the other has to be true in order for the statement to be true. For example, the statement, "You live in Wyoming or elephants enjoy being poached," is pretty brutal, but it is true because you do live in Wyoming or elephants enjoy being poached. Do elephants enjoy being poached? Probably not. So the second part here is false. But the first part is true, and because we're using the word "or," this statement is true, even though elephants don't enjoy being poached very much. So that's the difference between and or. For "and," both parts must be true in order for the statement to be true. For "or," one or the other must be true. This one or this one must be true. And if one of them is, then the whole statement is true. If I wrote "elephants don't enjoy being poached," now both parts of that are true, but the statement is still true. It was true to begin with. If I wrote "you don't live in Wyoming," or "elephants don't enjoy being poached," now this part is false, but this part is true. So therefore the whole statement is true. If I get rid of the "don't" here, "you don't live in Wyoming," false, or "elephants enjoy being poached," also false. So now this statement is false. That's how we use and or in the English language. You probably never really thought about that before, but that's how it's used. In algebra, the words and or have the same type of meaning. We're going to have situations where you wind up with x is greater than or equal to 2 and x is less than, let's say, 4. Can x be greater than or equal to 2 and at the same time be less than 4? The answer is yes, it can. So therefore this is a true statement. For the or side, we could have something like x is greater than or equal to 2 or x is less than 0. Could x be greater than or equal to 2? Say like 3 or 4 or 5? Sure. Would that make this part here true if x was 3 or 4 or 5? No, because x has to be less than 0 over here. But it does make this part here true, which means that the statement is true. When we graph "and" on a number line, I'm just going to use this example right here. I have my 2, so I'm going to put 2 here. I have my 4, so I'll put my 4 there. We've talked a lot about how you put your scale on a number line, and this is how I want you to do it for these types of problems. X is greater than or equal to 2 tells me I need a, hopefully you're thinking solid dot, and then greater than says up and to the right. For x is less than 4, I'm over at 4, less than means an open dot, and less than tells me up and to the left. What we are now going to graph here is the part that makes both inequalities true. So our first inequality is true only for values this way. Our second inequality is true only for values this way, which means that anything in between this 2 with a solid circle and this 4 with an open circle are true. So that right there is our answer. And statements will always look like that. They'll always have that sort of look to them. I'm going to go ahead and draw a number line for the or statement that I have here. X is greater than or equal to 2, or x is less than 0. So I need 0 and I need 2 for my number line. Greater than or equal to 2, solid dot, and then greater than says that way. X is less than 0, open dot, and then less than says that way. Or statements can look like anything, but most of the time they're going to look like that. It's possible to have an OR statement that does something like this. It's possible to have an OR statement that would be reversed to that. And it's also possible to have an OR statement that would do something like this, where both directions are true. In that case, what would the solution be? Hopefully you're thinking all real numbers. Sometimes you might get an AND statement that does something like this. If that happens, remember that AND statements mean that both parts have to be true in order for the inequality to be true. Is there ever a time when both parts here are true? This one going this way, this one going this way. The answer is no. So since both parts aren't true at any time, there is no solution in that case. And that's the difference between AND and OR algebraically. So do some practice problems here. These are called compound inequalities because we have more than one inequality involved in the same problem. Here we have this statement and this statement. So because of the word AND, both statements must be true. We're going to have to solve each and then graph both on the same number line. So here we go. I think we probably know how to do this at this point. I'm going to get x by itself by subtracting 1 from both sides, and I have 6 is less than 2x. And now to solve for x, we divide both sides by 2. 3 is less than x. Great. On this one, I have 3x is less than or equal to 18. Pretty easy to get x by itself here. X is less than or equal to 18 divided by 3 is 6. So I can draw my number line now. I need 3 and I need 6. So 3 goes here, 6 goes here. 3 is less than x is the same as, I'm reading backwards now, so pay attention, x is greater than 3. So I could rewrite this as x is greater than 3, and now I see that I need an open dot there, and then greater than tells me that way. For x is less than or equal to 6, I need a closed dot there, and then I'm going to go that way. So now we got to ask ourselves, where is their overlap? Where are both inequalities true? And the answer is from here over to here. So this right here is our solution. For the second one, this is also an AND statement. This is a compound inequality written in our very shorthand format. So what I would suggest you do, there's actually two ways you could do this problem. I'm going to show you the longer way here. What I would suggest you do is split this thing up. What this says is 3 is less than 5x minus 2, and 5x minus 2 is less than or equal to 7. Notice that I threw that and in there. So we have one part right here, and we have a second part right here. Those two separate things we separated out with the word and. So we have 3 is less than 5x minus 2, and 5x minus 2 is less than or equal to 7. It's a compound inequality with the word and. So now we just solve. Add 2 to both sides, and we get 5 is less than 5x. Divide both sides by 5. We get 1 is less than x, which means x is greater than 1. And over here, add 2 to both sides. We have 5x is less than or equal to 9. Divide both sides by 5. And I get x is less than or equal to 9/5. No big deal. A fraction isn't that much of a concern. So I need to draw my number line in here. I don't have a whole lot of room, so I'm going to squeeze it in up here. We need 1 and 9/5. So I guess 1's going to go on the right-hand side. 1. And then 9/5 over here, and then you just graph it. X is greater than 1, so that's an open dot, up and greater than. X is less than or equal to 9/5, that's a closed dot, up and less than is that way. This is an and statement, so we need the part that overlaps, and that's the part in between. So our solution is actually there. So we're going from here over to here, including 9/5. That's the answer. I want to show you the other way to do this, and I'm going to do that in this space right here. So for right now, we're ignoring this problem. The other way to do this, 3 is less than 5x minus 2 is less than or equal to 7, is to just go ahead and do this problem as is. I want to get x by itself. X is sitting here in the middle. I need x in the middle and everything else on the outside. So I need to get rid of that minus 2, which means I need to add 2. But if I do that and I leave the inequality like this, I must add 2 to everything. So I added 2 here, I'm going to add 2 here, and I'm going to add 2 here. That gives me 5 is less than 5x is less than or equal to 9. Notice that I wind up with pretty much the same thing. 5 is less than 5x. 5x is less than or equal to 9. 5 is less than 5x, and then 5x is less than or equal to 9. So we're doing exactly the same thing. It's just a little bit shorter. So now to get x by itself here, I divide by 5. But if I divide by 5 there, I must divide by 5 everywhere. So divide by 5 there, and divide by 5 there. 5 divided by 5 is 1, is less than x is less than or equal to 9/5. Now if you notice the way that's written, we have x sandwiched in between 1 and 9/5. And if you go up to the graph up here, the values that work, our x values, are sandwiched between 1 and 9/5. So this is sort of representing the exact same thing that we saw on the graph. Feel free to do your problems like this. Feel free to separate them out if you understand that better. But the graph will wind up looking the same, and that's what I'm going to be looking for in the answers. All right, so let's clear this off of here, and then you guys can try an or statement, and then another or statement. Go for it. Okay, for the or statement, we don't have anything pretty like we just did over here. It's just solve each one separately, and we want to get this variable by itself in both cases. So to do that, we're going to subtract 7 from both sides, and we have k is greater than or equal to -1. Or, don't forget to write the word. Here we subtract 8 from both sides, and we have k is less than -5. So then we draw our number line. We need our two numbers in there. And notice that -1 is actually bigger than -5, so -1 goes on the right, -5 goes on the left. Be careful about that. Hopefully nobody got tripped up by that just now. K is greater than or equal to -1. Greater than or equal to is a solid dot, and greater than is to the right, because these are the greater numbers. K is less than -5, so open, and less than -5 tells me that way. To the right. No, to the left. Yes. Anyway, we wind up with an or statement that looks like that, and that's exactly what or could look like. So probably we graphed it correctly. Next one over here, we have an or statement again, so we're going to stick with or, solve each one of these individually. Subtract 3 from both sides, and we have 7w is greater than 8. Divide both sides by 7, and we get w is greater than 8/7. Wonderful. Or, add 1 to both sides, and we have 4w is less than -12. Divide both sides by 4, and you get w is less than, still, because we didn't divide by a negative number, we divided by a positive number, -3. Draw our number line. -3 on the left, 8/7 on the right. W is greater than 8/7, so that's an open circle, and greater than values, so to the right. W is less than -3, so open circle, and less than, so to the left. It does wind up looking like an or statement, so we're probably pretty good there. That's it for the section. You can do the rest of the homework now. Good luck.